Lagrange multipliers. The concept of the Lagrange multiplier is similar to the idea of trying to find an extremum. Here, the point is to be able to maximize an area, a surface solid, with respect to another function or a constraint. What is the temperature, for example, within a vacuum, where the temperature or the heat ratio can be applied to a certain number, but based on the condition of that element, what is being allowed, whether by outside force or outside temperature or outside pressure, what is the maximum temperature for this particular containment. For an example, what is the maximum height of an airplane in flight with respect to the pressure, atmospheric pressure? The same thing with, say, for example, a submarine. What's the depth of a submarine in terms of that submarine being affected by the fluid pressure within the ocean, and as you get closer and closer to the ocean surface? Does it implode? When does it implode? At what mass of an object in volume can you predict or pinpoint mathematically when that would happen? These are all really good examples of a Lagrange multiplier in terms of finding maximum volume, the maximum area, the maximum the highest temperature, lowest temperature, or the pressure, and those kinds of things. For an example, here a very classic example given to us by Archimedes himself. I believe the one that he had was a circle that was inscribed by a square, and so the circle is inscribed by a square. What is the greatest area for a square inscribed in a circle where the circle has a known radius? Well, here, just a modification of that, you have an ellipse. If you know that the ellipse has certain dimensions, x squared over 9 plus y squared over 4 over 16 equal to 1, what is the maximum rectangle that can be inscribed therein? And the discussion of this could be not just restricted to the enclosure of the rectangle, but you can also circumscribe. What's the largest rectangle that should go on the outside as well? So we can use Lagrange multipliers in very neat fashions to be able to develop such an idea. The theorem of Lagrange says that if you're given two continuous functions, that is, their first partial derivatives are continuous, because that's what you're going to be using, whereas f achieves an extremum at some point x naught, y naught on a smooth constraint curve. Smoothness simply means that its first derivatives or first partial derivatives exist, and that the g function is not discontinuous on whatever interval that you're considering. So here f has some kind of extremum at a point on a smooth constraint curve that we call g, where g is said to be calculated to equal to some number c for whatever x and y. If the gradient of g at the point is not equal to 0, then there is a real number, lambda, such that the gradient of f at the point is equal to lambda times the gradient of g at that particular point. The method by which we solve is that here the first thing is you're going to find the find the first partial derivatives of f, set those to equal correspondingly to the first partial derivatives of g, here where g is multiplied by lambda. And then you look at the constraint equation itself, g of x, y equal to c, plug in those values from here, the first two parts, to be able to solve for x and y. Evaluate f at each solution point obtained. How many points you get, you consider. The greatest value would yield the maximum, or so-called relative maximum of f subject to the constraint, and the least value would yield a relative minimum subject to the constraint of g. Now let's look at some problems. It's very straightforward. Let's see if we can make some sense out of it. So here, use the Lagrange multipliers to find the indicated extrema, assuming that x and y are positive. So, like I said, we would find the partials of f and g. Here, this equation represents the g of x, y equal to c. So the partial of f with respect to x is 2x. The partial of f with respect to y is 2y. And then we need the partial of g with respect to x, gives us 1. Then the partial of g with respect to y is equal to 2. So according to the instructions, we set the partial of f with respect to x equal to lambda times the partial of g with respect to x. Then the partial of f with respect to y is equal to lambda times the partial of g with respect to y. And then we plug that information, or substitute this information, into the constraint equation. So if that be the case, we have 2x is equal to lambda times 1, or just lambda. Then we have 2y is equal to 2 lambda. Now, what that does for us, if you notice here, that this implies that y is equal to lambda, and then here we have x is equal to lambda over 2. So we're going to plug that information into g, that is x plus 2y minus 5 equal to 0. We can just say x plus 2y is equal to 5. So x is lambda, and I'll write my lambdas backwards because I'm left-handed and I think backwards. So x is lambda over 2. This is plus 2 times y, and y is equal to lambda. That's equal to 5. Just solve for lambda, and then from the solution for lambda, we know we can derive what x and what y would equal to. So here, if you multiply everything by 2, we get lambda plus 4 lambda is equal to 10. 5 lambda is equal to 10. Lambda is equal to 2. If lambda is equal to 2, then directly you get y is equal to 2, because y is set to equal to lambda. So y is equal to 2, and then x is equal to lambda over 2. That is 2 divided by 2, so we get 1. Now, this value that we get here, it's telling us that you want to minimize. We only get one point. So f of xy, where x is 1 and y is 2, yes, this is equal to x squared plus y squared. So this is 1 squared plus 2 squared, so we get 5. So here, the minimum is at the point x is 1, y is 2, and then z is equal to 5. And They're all just the same fashion. So the partial of f with respect to x is equal to lambda times the partial of g with respect to x. So this implies that we have 2x is equal to minus 2x times lambda so this is minus 2 times lambda x. Now what you get from that is that lambda, divide both sides by 2x, lambda is equal to -1. The next one, partial of f with respect to y is set to equal to lambda times the partial of g with respect to y. So here we get negative 2y is equal to 2 times lambda. Well, this implies that y is equal to negative lambda. Well, lambda is equal to -1, so we have y is equal to 1. Well, if y is equal to 1, can we solve for x? Well, yes. So we get y is equal to 1. The constraint equation is 2y minus x squared equal to 0. Well, if you know that y is equal to 1, that gives us 2 minus x squared is equal to 0. That implies that x is equal to plus or minus the square root of 2. So x is equal to the square root of 2. We don't need the -1 because up top it said that you want to assume that your answers for x and y are positive. So we don't need the negative part, right? And f of the square root of 2 comma 1 is equal to the square root of 2 to be squared minus 1 squared. So we get 2 minus 1 that gives us 1. So we have a maximum at the square root of 2 comma 1 comma 1. What about this next one? Here we want to maximize, so we find the partial of f with respect to x. That's 2 plus 2y. Then the partial of f with respect to y gives us 2x plus 1. We take the g equation, so we find its partial with respect to x. That gives us 2, and the partial of g with respect to y is equal to 1. So we set 2 plus 2y is equal to 2 times lambda. So here we have 2 plus 2y is equal to 2 times lambda. That implies, just dividing through by a 2, we get 1 plus y is equal to lambda. Now the next one, partial of f with respect to y is equal to lambda times the partial of g with respect to y. Well, that implies that we have 2x plus 1 is equal to 1 times lambda, or just equal to lambda. Well, if that be the case, well, since 1 plus y is equal to lambda and 2x plus 1 is equal to lambda, we set by the property of symmetry, we have 1 plus y is equal to 2x plus 1. So since 1 plus y is equal to lambda and 2x plus 1 is equal to lambda, this implies that 1 plus y is equal to 2x plus 1. And if that be the case, then y is equal to 2x, right? So if y is 2x, I plug that here, so I can solve 2x plus y is equal to 100. So 2x plus y is equal to 100. This implies that 2x plus 2x, y is 2x, is equal to 100. Here we get 4x is equal to 100, and x is equal to 25. So x is 25, but y was said to be equal to 2 times x. So y is equal to 50. And we go back to the original equation here to solve for f. And so we have f of 25 comma 50 is equal to 2 times 25 plus 2 times 25 times 50 plus 50. So we get 2,500 plus 100, so that gives us 2,600. So the maximum is that x equal to 25, y is equal to 50, and then z is equal to 2,600. All right. Find the partial of f with respect to x. Get 1/2 times 6 minus x squared minus y squared to the negative 1/2 times the derivative of the inside with respect to x. This is negative 2x. So we simplify that. That gives us negative x all over the square root of 6 minus x squared minus y squared. Very similarly for the partial of f with respect to y. This is negative y all over the square root of 6 minus x squared minus y squared. Now the partials of g with respect to x, that's 1. And the partial of g with respect to y is also equal to 1. So we have this. We have the partial of f with respect to x is equal to lambda times the partial of g with respect to x. So here, this implies that we have negative x over the square root of 6 minus x squared minus y squared is equal to lambda. Now for this one, the partial of f with respect to y is the same thing as lambda times the partial of g with respect to y. This implies that we have negative y over the square root of 6 minus x squared minus y squared. Here is equal to 1 times lambda. Well, since they're both equal to lambda, then we, by again the property of symmetry, or is that transitivity? A relates to B, B relates to C, and so A relates to C. I think this is symmetry. A relates to B, and B relates to A. Okay. So here, this quantity is equal to this. So this implies that negative x over the square root of 6 minus x squared minus y squared is equal to negative y all over the square root of 6 minus x squared minus y squared. Multiply both sides by a negative in the common denominator, and you end up with x equal to y. So if x is equal to y, come back and look at this constraint equation. So x is the same thing as y. So you can write this as x plus x minus 2 equal to 0. That is, 2x is equal to 2. That implies that x is equal to 1, which is the same thing for y. X and y are set to equal, right? So if that's the case, then f of 1 comma 1 is equal to the square root of 6 minus 2. So we get the square root of 4, and that gives us 2. So we have a maximum at x equal to 1, y equal to 1, and then z is equal to 2. One more. We find the partials. Right, the partials with respect to x, with respect to y, with respect to z. Then for the g equation, we find those partials. So now we set 2x equal to 1 times lambda, or just lambda. Then we get 2y is equal to 1 times lambda. Then we get 2z is equal to 1 times lambda. Now, if that be the case, then obviously x is equal to lambda over 2, y is equal to lambda over 2, and z is equal to lambda over 2. So we plug in these three values, the same values, into the constraint equation. So that gives us x, which is lambda over 2, plus y, which is lambda over 2, plus z, which is lambda over 2, is equal to 1. So that gives us 3/2 lambda is equal to 1. And so lambda is equal to 2/3. If that's the case, then we can solve for x, y, and z, because x is said to be lambda over 2, where here lambda is 2/3. This is 2/3 over 2. This gives you 1/3. That's the same. This is the same for y and for z. They're the same quantity. So now, if you plug in these values for x, y, and z, so we get x squared plus y squared plus z squared. Well, that becomes 1/3 squared plus 1/3 squared plus 1/3 squared, which is just 1/9 plus 1 over 9 plus 1 over 9. It just gives us 3/9 or another third. So here we have a minimum at x 1/3, y is 1/3, z is 1/3, and then its function value is 1/3. Well, I think that'll do it for now. Thank you.